These are problems 11, 12, and 13 on the kinematics review. These are all starred problems, so it might be a slightly longer video. Sorry about that. Number 11, an accelerating lab cart passes through two photogate timers 2.5 meters apart. That's our displacement. In 3.2 seconds, that's a time. The velocity of the cart at the second timer is 1.2 meters per second. A, what is the cart's velocity at the first gate? And B, what is the acceleration? What makes this one a challenging one is the first time we've ever had to solve for the initial speed, and a lot of times people just automatically assume when it's not given that it's zero, because that happens a lot in these problems, that you're not given the initial speed, that you're just kind of supposed to understand that if the car starts from rest or something, that it's going to be an initial speed of zero. That's not the case in this problem. In fact, it's even asking for what the initial speed is. So the initial speed is something, and we're going to find it. So that's the first thing we're going to do. We're going to look for the equation that does not have a in it, which is d equals 1/2 vf plus v naught multiplied by t. We're solving for v naught, so the first thing that we've got to do is we got to get it out of these parentheses. So first we got to get rid of the half, and we got to get rid of the time so that we can just not worry about these parentheses anymore. To get rid of the half, we multiply by 2, which is why there's a 2 in the numerator over here with the d. And we're going to divide by the time, which is why that is now in the denominator. That's just going to leave me with vf and plus v naught over here on the right side of the equation. And I'm going to subtract vf away, which is why I have minus vf. We're going to plug in our numbers. 2 times the d, which is 2.5 meters, all over time, 3.2 seconds, minus 1.2 meters per second for initial speed. And that's going to give us an initial speed at the first photo gate of 0.36 meters per second. We're now going to solve for the acceleration. We can use any equation because we have all of the other variables, and all of them have v naught in it. So I know in the previous problem I said if we can avoid using the thing that we solved for, we will, but in this case we can't. So we're going to use it, and simplest equation, the first equation, is vf equals v naught plus at. We're going to solve for the a, so I'm going to subtract v naught over to the left. That's why it's vf minus v naught in the numerator, divide by time. Now that's in the denominator. We plug our numbers in, and we get 0.26 meters per second squared for the acceleration. Of a 4 by 400 meter relay race, teammates pass a baton to each other. During an exchange, the runner receiving the baton is running with a speed of 2.3 meters per second. That's the initial speed until he grabs the baton. Once he grabs the baton, he accelerates to his maximum speed at a rate of 4.6 meters per second squared over a distance of 10 meters. How long does it take him to reach that maximum speed? T is what we're looking for. We're going to pick the equation without vf in it. That's d equals v naught t plus 1/2 at squared. What makes this a challenging one is not the physics. It's not the setup. Putting the numbers in this column is just as easy as every other problem we've had, and picking the equation is no more difficult either. The issue is that when we are trying to solve for time, and v naught is not 0, we end up having to do a quadratic equation for this. Now there is a way out of this if you do not want to do the quadratic, and the way out is to actually solve for vf first. The problem is not asking for it. You don't have to solve for it, but if you are really afraid of using the quadratic formula, that is an option. But we're going to solve using the quadratic formula because we're not afraid of it, and here's what you do. We have d equals v naught t plus 1/2 at squared. The quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. What that looks like when you use the kinematics equations and the variables is time, which is the variable we're looking for, that's our x, is negative v naught plus or minus the square root of v naught squared plus 2ad all divided by a. That's always going to work when we're doing the quadratic formula for this equation in kinematics. If you want to write that down on a note card or something, or on your equation sheet, probably not a bad idea. We can plug our numbers in. Time equals negative 2.3 meters per second plus or minus the square root of 2.3 meters per second, square it, plus 2 times 4.6 meters per second squared times 10. All that's divided by 4.6 meters per second squared. We have to do it with the plus and the minus, and that's going to give us 2 times, 1.64 seconds or negative 2.64 seconds. Now in math class, you would keep both of these because they could both be correct. In physics, however, we're talking about the real world, and we don't have such a thing as negative time. The runner did not reach his maximum speed in negative time. That doesn't make any sense at all, so we throw that answer completely out, and our answer is 1.64 seconds. Number 13. In a historical movie, two knights on horseback start from rest 88 meters apart. So you can see the distance written here in the picture. And they ride directly toward each other into battle. Sir George's acceleration, we're going to say this is George over here on the left, hence the big G. It's got a magnitude of 0.3 meters per second squared. Sir Alfred has an acceleration that has a magnitude of 0.2 meters per second squared. Relative to Sir George's starting point, so how far away from Sir George will the knights collide? This is a whole lot like the problem that we had with the Mythbuster cars, and we're going to solve it in a very similar way. We're just going to use slightly larger equations this time. So we have this acceleration of 0.3 meters per second, and this acceleration for Alfred of 0.2 meters per second. When we plug this one into our list of variables here, note that it's going to be negative because it's to the left. So I have two guys. I've got a George column, and I think was it Alfred or Albert? Tough to remember. But Knight A, look that up. It was Sir Alfred. Sir Alfred's column is over here on the right. So these are the numbers that I know. I know they both start from rest, so V0 is 0 for both guys. And the accelerations I've got, 0.3 meters per second squared for George, negative 0.2 meters per second squared for Alfred. Now I'm going to pick this equation, the D equals V naught T plus 1/2 AT squared equation for both guys. You might wonder why. Well, here's why. I'm looking for when their D's are the same, when their position is identical, when they've hit each other. So those two things I definitely want. That's what I'm solving for. So I want to pick an equation with those. So now that leaves me, do I pick the equation without VF or without time? I picked the equation without VF because VF for each guy is going to be completely different from each other because they're accelerating at different rates. But the amount of time that they're both moving since they start at the same time is going to be equal. So the time for George's equation is going to be the same as the time in Alfred's equation. So that's why I picked the equation without VF in it. It's the only thing that they do not have anything in common with each other. It's not the same for each guy. So on the left, D equals V naught T plus 1/2 AT squared. Notice a little G next to George's acceleration to denote that that is George's acceleration. V naught is 0, so that's going to go away, leaving me with D equals 1/2 acceleration of George multiplied by time squared. Alfred's is a little bit more complicated. D equals V naught T plus 1/2 AT squared. Again, we're using Alfred's acceleration, and again, his initial speed is 0, so I can cross this term out. But I have to add 88 meters because at time 0, if George is at position 0, he's at the starting line if this was a race, Alfred has an 88 meter head start. Now, yes, he's going in the opposite direction, but he is 88 meters away, and that has to be taken into account. That's the difference between talking about distance versus displacement, and in physics, we're talking about displacement. So we take that into account by adding 88 meters to his D, his position, his displacement, right from the get-go. So his equation, when we simplify it, is going to be D equals 1/2 Alfred's acceleration, time squared, plus 88 meters. Since both of these D's, the positions are the same because we want to know when they hit each other and are at the same spot, this 1/2 acceleration of George T squared and this 1/2 acceleration of Alfred T squared plus 88, these two things are equal, and that's where this line comes from. Everything over here on the right is going to be solving for time and then eventually solving for the position or where they hit each other. So we're going to solve for time up over here. I just rewrote that same line that I had so you can see what I do step by step. First thing we've got to do is get the times to the exact same side because that's what we're solving for. How long have they been riding until they hit each other? So I'm going to subtract 1/2 Alfred's acceleration time squared over to the left. So now you can see in this term, or this same equation, that now it's over here on the left side, 1/2 acceleration of George time squared, untouched, and I just move this one over, minus 1/2 Alfred's acceleration time squared equals 88. I'm going to factor out, there's a time squared in each one of these, so now it's factored, leaving everything else in parentheses. 1/2 George's acceleration minus 1/2 Alfred's acceleration. I'm going to divide the stuff in parentheses over to the right side, which is why in here I have 88 divided by the stuff that was in parentheses. But I don't want t squared, I just want t, so I take the square root. That's where that comes from. Now I can plug in my numbers. 88 meters divided by 1/2 George's acceleration of 0.3 meters per second squared minus Alfred's acceleration, don't forget about the half, times Alfred's acceleration, that is a negative 0.2 meters per second squared, and I find that it takes them 18.76 seconds to hit each other. From here, I can plug my time into either George's equation or Alfred's equation. I will get the same answer. I'll do George's just because it's a little bit smaller. So d equals 1/2 acceleration of George time squared. Plug in my time of 18.76 seconds, and I get the distance from George is 52.8 meters where they're going to hit.